So tomorrow we must move a little bit a step back and to go to talk again about rigid body motion. The reason is that when the placement is given by a rigid body motion, so when the placement of the point x is equal to the placement of one point x0 chosen plus an orthogonal matrix Q multiplied x minus x0, which is our formula of rigid placement. Okay, we have said that our density W of F has to be equal to 0. So as F is Q, because clearly the gradient of this linear affine map is Q. So in this case, F is equal to Q orthogonal. We have that W of every orthogonal matrix has to be 0. So no deformation energy for an orthogonal F. Okay, this is an important requirement for deformation energy. So when you have a sequence of rigid body placements, so when Q depends on T and you have different placements, so in different instance of time, you have different positions and different placements of the body. When the Q, the orthogonal matrix is varying with time, in general, you can also have that this position is varying in time. You have what is called a rigid motion. And all along the rigid motion, W of F of T is equal to 0. So the deformation energy is constantly equal to 0. And this is what we need to exploit fully in our discussion about the first variation of total energy. So in order to understand carefully how to use formulas for rigid placements, we need to give some extra details, and we will start this lecture doing this. So the motivation for going back once more to rigid body motion, which we have already discussed, is exactly this one. We need to study how the deformation energy depends on F. In particular, we want to understand clearly that the deformation energy is given by this integral, where here you have C, so F transposed F, and so the particle we have written in this way this formula because it was simpler to make calculations with F, the gradient of the gradient of key. However, these two formulas are not contradicting one the other. Why? Because W bar of C, being C a function of F with this simple relationship, this is our W of F. Okay, so what we have done up to now includes the case which is physically interesting, that is the case in which the information energy has this form. Okay, so I think that this is rather clear. So what I need now, I need to write this formula and I need to calculate its derivative with respect to time in order to find the rigid velocity field. And this is also very important for fluid mechanics. So we will try to discuss this also later, and we will need this also later. Okay, so we remark that this capital X and this capital X0 are independent of time. Why? Because you have your body in the reference configuration, you have one point X0, then you have one point X, and you fix the material particle X0 and you fix the material particle X. And you follow in time the trajectory occupied by X of the points occupied by X0 and X. Of course, this distance must remain constant. So my drawing is not very good, but okay. So we calculate the time derivative d over dt. Of course, here you have a time dependence. D over dt of key x. This is equal to d over dt of key of x0 t plus d over dt of q of t. And here you have x minus x0 because nothing else is changing with time. Okay. So I will not write all arguments now on, otherwise it becomes very difficult. I call this V, so V of x and t equal to V of x0 t plus Q dot, I call it, instead of this, I use this symbol, it means the same, x minus x0. But this is the map which to every particle x associates the velocity of that particle x. Now, what we want to write, a purely Eulerian formula. So we want to write, and this is rather difficult to understand. So let us spend some time on this. We have a body which is moving. we follow the motion of material particles. Then I place here in the position small x. And I want to write a formula which gives me the velocity v of the material particle, which at instant t is located in x, small x. So in different time instants, the material particle in x, so if you have t1 and t2, in different time instants, in small x, you have different material particles. Okay. However, I block my attention to the position small x, and I want to determine the velocity of the material particle, which at a certain instant is in small x. So this is the Eulerian description of motion. In fluid mechanics, usually you have a channel and you have a fluid flowing in the channel. So in every point, you are considering the velocity, which is the velocity of the material particle or of the fluid, which is flowing in x at small x at our instant t. Instead, when you write this formula here, key of x t is equal to key of x0 t plus q t x minus x0, you are, and the corresponding velocity v equal v0 plus q dot x minus x0. This is a Lagrangian description of motion. So you ride like jumping on the back of a horse, you ride a material particle x, so you choose x and follow x. Here instead, you choose the position small x and look what is passing there. So the point of view is different. Okay, in this Lagrangian description, you follow a certain material particle, and you follow the material particle. Instead, in the Eulerian description, you block the position and you look what is passing there. So we want to write, so this V is V of capital X equal V of capital X0 plus Q dot of X minus X0. And the independent variable is capital X. So we are Lagrangian. Okay. Now, if I want V of small x, I must change the structure of this equation. How I'm doing it? It is rather easy because key of x and t is small x. It is the position of the particle capital X. And key of x0t is the position of x0. Okay. Okay. So when I write key of x t equal key of x0 t plus q of t x minus capital X minus x0, I can find the material particle relative to small x simply solving this linear equation. So I write x minus x0 equal q of capital X minus capital X0. I multiply times q transposed both sides of this equality. As q transposed is equal to the identity, because it is orthogonal, we have this. So at the end, I have that x minus x0, capital X minus x0, is equal to q transposed small x minus small x0. This formula is telling us what? Given the position, I tell you which are the material particles in that position. Okay? So, this formula can be replaced here. So we can write this equation. And this equation is purely Eulerian. So we have that P in the point in the position X is equal to the velocity in the position x0 plus q dot q transposed, which is a function of time, x minus x0. This formula is probably in this form is due to Euler at the very beginning. However, the present matrix representation is most likely was written by Gibbs. Okay, so let's investigate a little bit. This is the formula of rigid motion in Eulerian rigid, better to say, to be more precise, of rigid velocity field in Eulerian representation. Okay. So we need to understand how q dot q transposed is made. So we know that q transpose q is equal to the identity. Okay. Imagine to be obliged to write q as a matrix and make all these calculations. Luckily, we have matrix algebra, so we can avoid making all these calculations in a complicated way because we have understood how matrix algebra works. Okay. So I have Q transposed function of time, Q function of time equal the identity, which is constant. So the idea is I calculate the derivative with respect to time of this. And Leibniz rule holds also for matrix multiplication. So I get Q dot times Q plus Q transposed times Q dot equals 0. So I'm brutally using the product rule for derivatives. So what I get that, remember that I need to understand what is the properties of Q dot Q transposed. Okay. So I discovered that Q dot transposed Q is equal to minus Q transpose Q dot. Okay. And by the rule of transposition, we have this. Because if you calculate the transposed, AB transposed is equal to B transposed A transposed. So if you apply this rule here, you get Q transpose, Q dot. Okay, let us write it. I get Q transpose, Q dot transpose, transpose, which is Q dot. Okay, so what we discover? We discover that this W is equal to minus W transposed. So this matrix is skew symmetric. Okay. Or equivalently, this matrix is skew symmetric. So we can write that in a rigid velocity field, the velocities are given by the following formula. V of x equal V of x0 plus W, depending on t, x minus x0, and W transpose is equal to minus W. Okay, so this should be sounding familiar to you, but maybe it is not. I need to add another ingredient, even if I don't like too much this extra ingredient, but probably you are familiar with this. So we must introduce the so-called Gibbs cross. If I have a skew symmetric matrix W, and I calculate W of a vector applied to a vector V, this is equal to vector omega vector product V. In reality, this is a definition of omega and of cross product. So we can say in this way, for every W skew symmetric, there exists a unique omega such that for every V, W applied to V is equal to omega vector V. So in a sense, instead of writing a skew symmetric matrix applied to a vector, I prefer to introduce omega, a vector, and to invent vector product in such a way that this equality is valid for every W. Okay, so I give you to solve this problem. So given W, the matrix, so given the components W11, W12, W13, W22, W33, W23, and you have minus W12 minus W13 minus W23. It is skew symmetric. So in the main diagonal, in the principal diagonal, you have all zeros. And you calculate this first product, then you write omega vector V, and you apply the standard rule for calculating this vector. And for instance, you remember you have the rule E1, E2, E3, omega 1, omega 2, omega 3, V1, V2, V3, and you calculate formally this determinant. Okay, so given W, you must find the components of omega. It is a trivial computation, but please do it so you are persuaded that what I'm telling you, so that I repeat that every skew symmetric matrix determines a unique omega. The vice versa is also true. Is a correct statement. So omega is called the Gibbs Cross for W. Okay. So what can we do? We can rewrite this formula V of x equal V of x0 plus Wx minus x0 in another way. V of x is equal to V of x0 plus omega vector x minus x0. And I'm sure that this formula you have already seen. Okay. So we needed some algebra, but we have understood how the velocity field in a rigid motion is so if delta k is v of x times delta t, so if I consider a small placement obtained multiplying times delta t a rigid velocity field, let's call it rigid. Okay. What I have. So let us try to understand what we are doing. I have the equilibrium. Okay. The equilibrium configuration, which is the minimum of energy. So the first variation of total energy is 0. Okay. Then I consider a small variation of this equilibrium configuration. Delta K can be regarded either delta K can be regarded either as a function of capital X or delta K can be considered as a function of small x. So I can introduce either, this is the placement delta, displacement delta K of the material particle X, capital X, or I can regard it as the displacement of the material particle capital X, which is in small x. So this is equal to delta K minus 1 small x. So I am here, small x. I go back to capital X. I consider the variation delta K here, and I calculate the displacement in small x related to the Lagrangian variation of displacement delta K. Please be careful in understanding this reasoning, because this is the standard form of argument in fluid mechanics, which is rather difficult to understand if you don't follow carefully the change from Lagrangian to Eulerian descriptions. Okay, very well. Now, I consider this delta K of small x given by this formula. So I have V rigid of x0 dt delta t plus omega delta t vector x minus x0. So this we can call delta displacement of x0, and this is delta theta function of t. Okay. Now, why I'm calling this delta theta as I usually call a variation of an angle? Because this W is Q dot Q transposed and Q maps capital E1, capital E2, capital E3 into their actual configuration, if you remember, in a rigid body motion. So this is Q, gives you a three-dimensional rotation of the rigid body. Okay. So W describes you the Eulerian speed, better to say velocity, the Eulerian velocity of orientation. So sometimes this is called angular velocity. Okay. So we want to suggest that the angles giving the orientation of the body are changing a little bit. So we have that delta key x equal VR, delta U x0 plus delta theta. Of course, here you have t also, the at our instant t, vector x minus x0. This is an admissible small or virtual displacement. Which can be used in the condition delta E dot equals 0. Okay. Now the delicate point. So now we go back to our reasoning of yesterday. Yesterday we introduced the constrained forces for replacing the essential boundary condition. So I remind you what we said yesterday. If key star is the unequilibrium configuration, for the total energy given by this so we include dead loads in volume and dead loads on the surface. So this is the volume and this is the surface. Okay. And this is for free, only for the free part of the boundary, with essential boundary conditions. Key given on the boundary of C star minus the part of the boundary which is free. Okay. Then key star is, okay, then there is a field B sigma constraint in the boundary of C star minus the boundary free, such that key star is minimum of E tot given by integral of W F plus integral on the boundary of C star, minus B volume key plus integral minus B sigma C key, where we had previously applied essential boundary conditions, and the standard, the already applied surface forces on the free boundary. Okay. Remark. This is the minimum double star. This is the minimum star. If we have a minimum double star of star, and we add a rigid placement, and we call it key star, and we add a rigid placement. So we write key star plus key of x0 plus qx minus x0. This key tilde star, the field key tilde star, is also a minimum of double star. So what I'm telling you is that when I relax the displacement conditions, so if I don't block 3 points on the boundary, one equilibrium can be translated and it remains an equilibrium. Okay. So the idea is I have a body and it is in the actual configuration in equilibrium. So the body is in equilibrium. So I have a C star, I have a placement, and this placement is an equilibrium placement we have called key star. Okay. Assume that we had given the displacement of one part of the boundary. Okay. Now, this replacement, for the moment, we can call replacement lemma, tells you that you can forget about the essential boundary conditions. So you don't give the displacement, but you replace essential boundary conditions with B constrained sigma, B constrained sigma. And you keep B sigma as before. The equilibrium with this new set of boundary conditions, which are all natural. So we replace essential boundary conditions with suitable natural boundary conditions. And as we said yesterday, we don't know, it is unknown, the set, the field of constrained forces. Okay. So we replace with suitable natural boundary conditions the so-called constrained forces. Okay. And what we say is that modulo a rigid placement, so we can translate and rotate the body, the solution of the first problem, where you blocked a part of the boundary, which includes 3 points. So you block 3 points. The first problem can be replaced by this other problem, where only forces are applied on the boundary of your body, plus volume forces. Okay. So we can write, if we accept this lemma, the equilibrium conditions, the equilibrium equations, as follows. For every delta key, integral of dw over df delta f plus integral over c star of minus b volume delta key plus integral over the whole boundary. Now I don't make distinction between forces applied on the free boundary and constrained forces. So I write B total sigma delta k. This has to be equal to 0. Okay. Now let us consider this when delta k is equal to delta u0 plus delta theta vector x minus x0. Okay. Now we remember that in reality this equality is this quantity is dw over dc. Then you have dc over df delta f. Okay, this is the true, because w of f is equal to w bar of c of f, because there is no deformation energy when f is rigid. Okay, so we can call this is actually delta c. Okay, so to write it clean, maybe it is better if I write it clean. This is equal to dw bar over dc delta c. Okay, but this delta c is relative to this rigid body motion. Okay, so I have f transpose f, which is c. Okay, then I change delta key, so I have key plus delta key. Okay, so let's do the calculation slowly. Grad key plus delta key is equal to grad key plus grad delta key. Okay, or if you like, remembering that we can commute delta with grad, delta grad key. Okay, so this is f plus delta f. Okay, so delta c is equal to f plus c plus delta c is f plus delta f transposed f plus delta f. Okay, so what we need to calculate is delta c. So I must subtract to c plus delta c minus c. So I continue this calculation, and I will estimate this variation of c. What I want to deduce is that delta c is equal to 0 when delta key is given by delta u0 plus delta theta vector x minus x0. Okay, so what I get? I get f transposed plus delta f transposed times f plus delta f. So I get this times that F transpose F. Then I get plus delta F transpose F plus, so I'm doing this times that, then this times that, then I get plus delta F, sorry, F transposed delta F plus delta F transposed delta F. Okay? This is an infinitesimal of higher order. Okay? So what I get, and I can't neglect it, so I get that C plus delta C is equal to C plus delta F transposed F plus F transposed delta F. Okay? If my calculations are right. Okay. Plus delta F transpose delta F, which is negligible. Okay. Very well. So delta C is nearly equal to delta F transpose F plus F transpose delta F. And this is symmetric. Okay. Okay. Now F is equal grad delta K. So let's go to this expression. Okay. So delta K is equal to delta U0 plus a skew symmetric matrix X minus X0. Okay. Grad delta K is therefore equal to W. This is rigid motion. Okay. So I can replace a skew symmetric F inside here. And this is clearly equal to 0. Okay, because this is symmetric. So even if I'm running too much in this, try to reconstruct this reasoning. In case you have troubles, we can reproduce it once more. Maybe I'm running too much, but so at the end, this first variation is 0 in the particular case of this delta K here. Okay, so we are left with the equality. For every delta U0 and for every delta theta, the integral over the volume C star of B volume delta U0 plus omega vector x minus x0 plus integral over the boundary of C star of B sigma total du0 plus omega vector x minus x0. This is the volume, this is the area, is equal to 0. Remark that minimization condition implies this. Why? Because the opposite is not true. Why we have this? We have this because not all delta keys are rigid. So the minimization condition says that delta E dot for every delta key calculated on every delta key is equal to 0. Set of delta keys, rigid delta keys. Okay, so you cannot hope that the vice versa is true, because you are using only virtual displacements which are not deforming the body. You find, so what we do, we find necessary conditions for equilibrium. And only in particular cases, these necessary conditions will be sufficient for equilibrium. Okay? So this has to be clear. Okay. Now, this formula, I want to make for you the list of all difficulties, because we must understand, try to understand. By the way, the selection of these subjects I've done for helping you in using COMSOL. So these theoretical things will be important for your understanding how the code works. Okay, now I want to replace in these integrals the variables. So instead of calculating, consider that this is a scalar quantity. Okay, so I can easily change the variable here. So I can write this integral in the actual configuration. Of course, I need to change also the volume. So I will need a Jacobian determinant times the, okay, I was wrong. I had to place here the star and the sigma star. Okay. So dv star in the reference configuration is equal to j dv j minus 1 dv. you change the variable and you need a Jacobian determinant. And here we can replace the area. So we have a density, let's call it J superficial. In this moment, the value of this is not important, d sigma. So this is d sigma star. For having the same notation, I write J minus 1. Okay. So transforming the volume density Eulerian, Lagrangian, into the Eulerian volume density and the surface density Lagrangian in the surface density actual. And this is the so-called change between nominal value of applied forces to actual value of applied forces. Because if you have a force applied per unit area in the Eulerian description, the area is changed because you have a deformation in the Lagrangian description. Okay, so when you deform a body, this area changes and it becomes there. If you have a dead load, the force here and the force there is the same. Unit area changes because of the change of the area. And the same happens for the volume in the change of volume. So you can rewrite our equality for delta theta here, delta theta there. So our equilibrium necessary, our condition necessary for equilibrium rewrites integral over C star of B J minus 1 BV dot delta U0 plus delta theta vector x minus x0 plus integral on the boundary of C star of J sigma minus 1 B sigma delta U0 plus delta theta vector x minus x0. This is equal to 0 for every delta U0 and for every delta theta. Okay, so what I do? I consider delta theta equals 0. I start with this. And what I get? I get integral over C star of J minus 1 BV dot delta U0 plus integral over delta C star of J minus 1 sigma B sigma dot delta U0. And this is equal to 0 for every delta U0. This delta U0 is constant, so it is all the same for every material point. So I get 0 equal delta U0 inner product integral over C star of J minus 1 BV plus integral over the boundary of C star J minus 1 sigma B sigma.
But this is a C star or C?
Sorry, you are right. You are right. I did everything for changing into the Eulerian, and I'm writing wrong. Grazie. So this is true here. Okay. You know, I changed the variable and then I forgot the change of variable. Okay. So at the end, do you remember what is this? This is the resultant force by definition. This is the sum of all forces applied to your body. Okay. And we have deduced that for every delta U0, this resultant force, inner product delta U0, is equal to 0. The only vector which is orthogonal to every other vector is the null vector. So we have proven, as Euler did, the so-called first cardinal equation of dynamics. In equilibrium, the resultant of all applied forces is 0. And we have proven this equation starting from the principle of minimization of energy. And it is a necessary condition for equilibrium. Okay. Now we will check what happens for delta theta different from 0 in the next lecture. Look, I think that I will repeat this lecture and the previous one another time, because this subject is very delicate. Alessandro, stacchiamo la registrazione. But I hope that